using microphones, and I'm a very loud person, so I'm just going to project until I turn over to Quang. So I'm Ron Yurko. I'm an assistant teaching professor, statistics, data science here at Carnegie Mellon University, along with Department Head Rebecca Nugent and also affiliated faculty Sam Ventura, who you will likely meet tomorrow. We're part of the organizing committee of the conference. Very happy to have all of you here. We've started doing this a number of years back with a workshop event to kick off the conference. And we've been fortunate enough last year and this year to do it around the theme of the NFL Big Data Bowl. All right, so if you don't know what it is, that's great. You're gonna learn all about it today. And so before that, just a reminder, internet, connect to the CMU Wi-Fi if you have not done so already. All right, this is the same Wi-Fi code you'll use throughout the weekend. And any other logistics before I turn it over? Okay. So the instructor, speaker for tonight's workshop is a finalist from last year's NFL Big Data Bowl. He's a second-year stats PhD student here, Quang Nguyen. So he's gonna talk all about getting started with the NFL tracking data and the Big Data Bowl, the project he implemented last year that was a finalist contention, and then also just things to keep in mind as you're starting to work on it if you're a student or someone external wanting to dive into the data. All right, and at this time, I'll turn over to Quang, but if you have any questions, some of us will be in the back. Feel free to raise your hand. I can pop by, help out. Otherwise, let's thank Quang for putting this together.
All right, thank you, Ron. Before we get started, just a quick note, if you want to access the slides, you can go to the conference website. This is 2023. You can go to November 10th, which is today, and you should be able to access the slide right here. So there you go. That's how you get the slides. All right, let's get started. Full screen. All right, so here's a quick agenda for today. Today I'm going to give you an overview of a big data bowl project, specifically a metric track project, from start to finish. So I will be providing a detailed walkthrough of all the steps involved in this project. So what should you take away from this workshop? So first, not necessarily the code. Okay, it's good if you get all the code and everything, but not necessarily the code. But primarily, I want you to focus on the entire process and all the concepts involved, because the code is written in R, but if you understand the methodology and all the steps in the pipeline, you should be able to implement it using whatever language you prefer, Python, Julia, etc. And also, I want you to be able to learn how to present the results. So you can learn how to tell different stories with your data visualization, things like that. And also, lastly, although we're doing it for American football, the metric itself and also the entire process of building the metric can be applied to all kinds of sports, not just football. So keep that in mind as well, because this should be able to, the whole process should be able to be generalized to different sports. All right, so as Ron said, today I'm going to give you an overview specifically on how I developed my metric, specifically a pass rush metric for the Big Data Bowl 2023 from last year. That's going to be our case study for today. All right, so here's a quick outline of this workshop. As a quick appetizer, I'm going to give you an overview of the Big Data Bowl competition and also the provided tracking data and all the data set that they provided, and also how you can do basic tasks, including data pre-processing visualization. And then we're going to move on to our main course, which will feature the motivation and the formulation of the metric, and also different types of things you can do to present your results and validate your result, things like that. So that's the outline. All right. So first, let's talk about the Big Data Bowl. So if you don't know anything about it, the Big Data Bowl has become the premier sports analytics competition And specifically, the competition focuses on player tracking data. So the data are collected at a rate of 10 hearts, or more specifically 10 frames per second, using RFID chips placed inside of player shoulder pads and ball. And these are all tracked by the tracking system known as Next-Gen Stats. And so every year, the National Football League, specifically the data analytics team led by the legend Michael Lopez, releases a sample of player tracking data and with a competition theme. So the competition has been going on for 6 years. This is year 6. So it started back in 2019. Back then, it was the inaugural competition. I think it was hosted on GitHub, and there's like an email you can submit it to. So back then, most people ended up doing some sort of receiver evaluation. But since year 2, since 2020, the competition has been hosted on Kaggle. And the theme has evolved a lot over the years. Back in 2020, that was the only year that there was a straight-up prediction competition where there's an evaluation metric and you just try to build the best model as possible. But for the remaining years, later on, the competition theme is more open-ended, where you can focus on different aspects of football, and it's not necessarily a competition, it's more of like a open-ended type competition. So back in 2021, it was defensive performance on passing plays. 2022, special teams performance. 2023, which is what we're going to focus on today, which is last year, which is linemen on passing plays. And this year, the theme is something that we haven't tackled before, which is tackling. So it's 2024. All right, so in terms of the tracks, so for 2024, there are 3 total tracks. The first one is undergraduate, or formerly known as college. So if you are an undergraduate student, if your team consists of all undergraduate students from your institution, you should be able to enter this track. And then we have a metric track, or formerly known as an open track, where if you're a graduate student, you work in industry, etc., you can enter this track. And since last year, the NFL has allowed for a new track called coaching presentation, where you can sort of tailor your big data submission towards a coaching personnel. You can work with a coach, but it's optional. But your submission should be easier to understand and should help the coaching staff in general. In terms of prizes, so since 2021, the total prize is a total of $100,000, but the distribution is slightly different across the years. For 2024, feel free to check out that link. I think if you end up in the top 5, you get 12.5K, and you get invited to a combine to present your submission and try to win a grand prize. And then out of those 5 finalists, there will be at least 1 from each track and 2 more wildcards. So keep that in mind. All right, so that's a quick overview of the Big Data Bowl. Let's now talk about the data that are provided by the competition. Okay, so what are the provided data set? So obviously we have player tracking data, which I just described before. Data collected by putting chips inside of players in the balls, players' shoulder pads in the balls. And also we also have some contextual data, which is game, play level, etc. I will go more into detail in the next few slides. If you want to learn more about all of these, and more importantly, if you want to follow along, running all the code and all of that, feel free to get the data for today's slide using that link right there. You can read about a more detail of the description of all the variables in the dictionary as well. And that data set is pretty similar for 2024. Might be some different variables, but overall, the set of data are the same. Okay, so first we have the game data. So this is just basic game level information. So each game has its own identifier, and also there are other variables in this data set. So the season, the week, the date, the time, let's see what else. And then who are the home and away team? Very, very standard game level information. Next, we have the play level information. So first we have, again, identifier for the game, which we can match this with the game table, and also a play ID within each game. And then a description of, so this is what you typically see in like the play-by-play if you go to like the football website. And then these are the context of the play. So the quarter, the down, yards to go, team with the ball, who's the opposing team on defense, game clock, pre-snap home score, etc. There are plenty more information about the play, like who got the foul, what are the personnel, what is the formation, etc. We also have info for the players, so player ID, the height and weight, birthday, where they play in college, official position recorded by the league, and the display name. Since 2022, so started 2 years ago, the Big Data Bowl also provides PFF chart information about players in the play. So for last year, we have, again, this is chart information, so for each player within the play, within the game, we have their role, so whether they're passer, pass blocker, pass rusher, etc., and then position when they line up, and various other information that were charted by PFF. So hit, hurry, sack, that would be helpful later on, etc., many more. And lastly, most importantly, we have the tracking data. So specifically for last year, we have a total of 8 weeks of data, so week 1 through 8 of the 2021 regular season. For this year, I think it was week 1 through 9 of the 2022 season. But we're using data from last year. And all of this sort of represents a real play in real life. So I'm going to show you a play first. So this is the play that I will be using throughout this workshop to demonstrate various things. This is the play from, I think, week 6 of 2021 NFL season, Raiders versus Broncos, where Broncos quarterback Terry Bridgewater is sacked by Raiders defensive end Max Crosby. And going back to this table, all of these variables are recorded for Max Crosby, just an illustration. So we can see the jersey number, the team that they're on, play direction, and this is what we were interested in. All of the location information, physical attributes of that player throughout the course of the play. And again, they are recorded at a rate of 10 frames per second. So here we have X and Y locations, speed, accelerations, distance travel from a previous frame. Let's see, orientation, angle of motion, and we also have the event annotation associated with each one of these timestamps. So we know whenever it's a ball snap, whenever there's like first contact, whenever there's being sacked, whether it's a pass forward, etc. And this can be key later on when we try to filter out all of the unnecessary frames that we don't need. So keep that in mind. So that's the tracking data set. Okay, so the first thing I want to talk about is, so we have that data. It's the basic form, raw data. The first thing we want to do, we want to standardize the data. What I mean by this is, so in the raw data, if you notice, there are 2 play directions with respect to the offense, left and right. So if we go back to this table, tracking, for this specific play, the play direction is left because you can see the play is going left. So that's the direction. But we need to standardize the player tracking coordinates so that the offense is always moving in the same direction. Okay, and this can be helpful later on for all of your feature engineering tasks and also modeling tasks. Okay, so what I mean by that is you need to, we're going to make everything go from left to right for the rest of, for all of the plays. So we need to flip the X and Y coordinates of the players, and also we need to flip also the direction and orientation so that if a player is moving 0 degree, that means that they're moving left. If it's 90, then they're heading towards the opposing team's end zone. If it's 180, then they're moving right. And if it's 270, that means that they're moving backwards. Okay, so now I'm going to show some code for how you can do that. So I first reading the data. So if you want to follow along, feel free to get the data. And here, notice that I store all of these data in the same directory as the source file. So there's no subfolders or anything. All everything's in the same folder. So I read in all the data. I load the tidyverse, which I'm going to use throughout, setting the theme for my plotting. And notice that there are 8 separate files for the 8 tracking data set I made. I decided to bind all of them together using, I detected their pattern, which has the keyword week, and then I just bind them together. Okay, so after we bind them together, we have a full tracking data set. And we just need to flip the direction and orientation, and also make all plays go right to left, or left to right, excuse me, that I mentioned earlier. And this is just very simple geometry. We're just reflecting everything across the horizontal and vertical axes for the X and Y locations, and with the direction and orientation, it's just simple calculation, so feel free to check it among yourself if you don't believe me, but it should. So that's how you would standardize the field for all of the plays in the data. Okay, so that's the first basic data pre-processing task. Now what I'm going to talk about is how you can first plot this data and have a visualization for it. So the tip for doing a big data project in general is that you should pick out an example play as a case study throughout the project so you can demonstrate, for example, your metric, how can you use that in that specific play, something like that. So here I'm using the same play that I showed earlier from week 6 of the 2021 season, the play where Max Crosby of the Raiders ended up sacking Teddy Bridgewater of the Broncos. And again, here are just the variables I mentioned earlier for that specific play. All right, so in terms of plotting, so here I'm going to use something called SportyR, which is a great package for creating surfaces for all kinds of sports. I think SportyR and its Python counterpart, SportyPy, kind of underused in my opinion. I think people should be using them more because they're very useful. And within SportyR and SportyPy, there are many other different surfaces you can use for many other leagues as well: hockey, basketball, soccer, etc. So in terms of plotting, the sort of, I guess, theory here is that you start with a base layer, and then you can you keep adding different layers to it. It's just like you're trying to paint something. You start as a blank canvas, and you just keep adding things to it. So here I'm setting up first my base layer, which is an empty football field. So here, these are just the code that I took from the documentation of SportyR for football. Notice that I only keep the inbounds, and also I just limit the field to the specific regions of interest that I'm gonna display the play for. And also I want to change the color of the surface to I chose spring green 3 because the default color is a little bit dark and not particularly a fan of it. So, but you can change to whatever color you want. There's a flexibility for that. And if you print this out, you get this surface right here. So that's the first step, setting up the background with nothing else on it as the base layer for plotting when you want to visualize the data. Okay, so the second task here is to actually visualize it. So here what we can do is we can get the play that I mentioned earlier using its game ID and play ID, and then get all the X and Y positions for all the players on the field at each time frame, and then just animate it throughout the course of the play. So here, again, I filter out the play ID in the game ID, and also I assign different colors to different teams. So for Denver, I put navy. For Vegas, I put white. And for football, I put yellow, just for it's too easy to see. Because technically it's not really yellow. Okay, so and then I just start plotting, adding a basic point layer to it. Notice that since I already flipped the X and Y and the play is going from right to left, I just sort of mirror it again and make it so that it reflects the real life direction. And I assign the color to each of these points. Then I added an animation layer, which help us depict this play, depicts all the action throughout this play over the course of it. So we can see all the play movements at the ball snap. It's quarterback's trying to throw a pass, and then he ended up getting sacked over there. So we can sort of illustrate all these action with this sort of animation. Should be really useful. All right, so that's the first basic task of what's the data, how can you pre-process it at an initial step, and also visualize it. So now I'm going to move on to the actual, the main topic of today, which is how do you actually build a metric. Okay, so again, the goal is to build a metric to evaluate pass rushers in the National Football League. So first I want to talk about performance metrics in sports in general. So performance metrics based on tracking data can be classified into two different types. The first type is directly derived, where you can just directly derive those from the data. So, all of the distance features, the distance between all the players, those can be directly derived without fitting any models. The second type is something called model-based, where you build a statistical model, and then you can let it spit out some output, and you somehow summarize it, aggregate it, and then you get some measure of player evaluation. So what people typically do is that they just, take a kitchen sink approach where they just create a bunch of features, they just ship them all into a black box, things like that, and then boom, spits out something. Which is sometimes good, but should be careful about that. But again, these two are the two different types of metrics based on tracking data, directly derived and model-based. For today, our proposed metric is directly derived. So it's something to keep in mind. And if you want to learn more about, read more about all of this performance metrics based on tracking data, and also you want to learn about player tracking data in general, feel free to check out this great review paper by Stephanie Kovacic, which got published in the Annual Review of Statistics this year. So I have included a link here, so feel free to check it out. It's a really great paper to read if you're interested in tracking data and want to learn more about it. Okay, so before I start talking about our actual metric, I want to quickly mention two links. So for this project, we have our Kaggle notebook. Feel free to check it out. You can see all of our submission for the Big 3 Bowl for last year. And also, we have followed up the submission with an paper, which got published in the American Statistician a few months ago. So you can also check it out on archive for free as well, for a full version of the paper. Okay, so let's now talk about the metric. So again, the goal is to build a metric to evaluate pass rushers in football. So first we want to think, right? How do we actually measure pass rusher effectiveness? So when we think about that, there are two things you need to consider, right? As the simplest form. Two features. First, distance to the quarterback, right? If you're close to the quarterback, that should be good. And also, the speed that you're moving towards the quarterback. If you're moving fast towards the quarterback, then there's a high chance that you should be able to put some pressure on them. So you want to think simple about this. So ideally, this measure should increase as the speed increases and as the distance decreases, right? You want to be closer to the quarterback, and you also want to approach the quarterback at a fast rate. So what if we just consider speed divided by distance? So if I were to write speed divided by distance, now we want to analyze just simple, like what's the unit of this quantity, right? For speed, say it's yards per second. For distance, it's yards, right? And the unit would cancel, so you end up with something that is 1/2 or inverse second, something like that. So what my collaborator did was, he went on in Google inverse second. That's what he did. And then he found this Wikipedia page, and on it, he skimmed through all of these different concepts from various different fields. And then he found something called strain rate from material science. And he clicked on it and read about it, and he thought this makes sense to the context of football, and this is what we went with. I'm going to show you more detail in just a second. All right, back to the slides. Just delete this. So we found that concept strain rate. So that's going to be the basic of our metric. Okay, so what is strain rate? So what I'm holding in my hand right now is a rubber band, okay? So in material science, the action of stretching a rubber band illustrates the concept of strain rate. The strain rate is defined as the ratio between two quantities. The speed at which the two ends of a rubber band are moving away from each other, I just broke it, and the original length of the band. So how does this connect to pass rush in football, right? So as we just mentioned earlier, we believe that the two most important features for evaluating how effective a pass rusher are how fast they're moving towards the quarterback and the distance between the pass rusher and the quarterback. Those two features happen to be the exact same two dimensions required for the calculation of strain rate. Moreover, we also find a delightful analogy that in material science, the strain rate illustrates how much a material deforms from its original size with respect to time. This corresponds to a pass rusher trying to put pressure to deform the offensive line to get to the quarterback. So the players can be viewed as particles in some materials, and the defensive particles are trying to put a strain on the offensive line to get close to the quarterback. So that's the I guess, cute analogy that we found. So, inspired by the concept of strain rate in material science, we created a metric called strain in all capital letters. So the definition of our metric is as follows. So for every pass rusher, at each frame within a play, we want to calculate the following quantities. First, the distance between the pass rusher and the quarterback, which you can get using the XY location, using your simple formula, Euclidean distance you learn in Algebra 1 or whatever. And then the velocity at which the pass rusher is moving towards the quarterback. And you can think of this velocity as the instantaneous velocity, which is estimated by the rate of change in distance between the current and previous frames. So it's just the differences between the two frames of distance divided by the change in time, which is 0.1, because we're recording the data at a rate of 10 frames per second. And a metric strain is just simply a ratio of the aforementioned velocity and distance quantities. However, we have a negative sign in front. Why is there a negative sign? So going back to the rubber band example, in that case, a positive value of strain rate corresponds to when the two ends of a rubber band are moving away from each other at a fast rate. However, in our football setting, we want the metric to be positive when the defender is getting closer, not further away from the quarterback at a fast rate. So that's when the negative sign comes in. All right, so this is the entire formulation of our metric, borrowing the concept from material science. Just a simple equation of d divided by d with negative sign in front. Okay, so and it turns out that a metric has lots of great properties. First, it is simple since it does not require any complex modeling such as the neural nets, the XGBoost, the random forest of the world to compute it, and instead, strain just simply a directly observed measure of pressure as a function of only two features, distance and velocity. A metric is also interpretable. So recall that strain is velocity over distance, so unit is again 1/2 So if we were to take the inverse of that, we just take 1 divided by strain, we get a measure of time, right? Because it's 1 divided by 1/2. We flip, it's just seconds, which is time. And in particular, it's the time required for a pass rusher to get to the quarterback, given the current velocity and distance from the quarterback. And we find it's very intuitive and very easy to understand. Also, it is scalable. It literally can be applied to every passing play, minus some trick plays, like say you have like 2 quarterbacks on the field, so I guess no Taysom Hill here because we need like a uniquely defined quarterback for the calculation of our metric. And also, you can apply this to other settings too, not just quarterback. You can apply to, for example, to this year's theme, tackling, right? It could be a very useful feature for your tackle probability model of seeing the amount of pressure that every defender is putting on each ball carrier, for example. So keep that in mind. Also, strain provides a continuous time within play measure of pressure, which addresses the shortcomings of previous pass rush metrics. So what were the previous metrics? So traditionally, we have, sacks, hits, hurries. Those have been collected for a long time. But those are just counting statistics, which means that we only observe them at the end of the play. Okay, there's no continuous element there, just discrete time quantities. Also, previous metric could also be based on some sort of arbitrary subjective judgment. So ESPN has something called pass rush win rate, which is a great metric, by the way. I mean, it was created by tracking data. So that's a great step compared to the previous statistics like sacks, hits, or hurries. However, pass rush win rate is a little bit subjective in the sense that it only illustrates the ability of a pass rusher to beat the blocking matchup within a certain time pressure. I think they chose 2.5 seconds. So, but however, our metric sort of addresses all of these shortcomings and provides a granular measure of pressure at the continuous time within play level. Okay, so now those are the background of our metric. I want to show you how to actually implement it using the tracking data rules. So what are my steps here, right? First, so having just all the raw data for now with a little bit of pre-processing that I mentioned earlier, I want to first filter data to keep only the frames between the ball snap and a QB event. So that QB event could be a sack, a pass forward, a fumble, etc. We don't care about what happened before ball snap or after the quarterback gets sacked or the pass got forward. We can then identify the locations of the passer, the QB, and also all the players that were labeled as pass rusher by PFF within the play. And then, once we have all this information, we can then calculate the distance and velocity quantities I mentioned earlier, and then just, let velocity over distance and we get strain. So here are all the steps we need to do to implement the metric. Okay, so here's some code of doing that. So I would start with identifying the start and ending events of each play. So as starting events, you can have ball snap or auto event ball snap. And for ending event, as I mentioned earlier, we have pass forward, QB sack, fumble, etc. So here are all the possible ending event that you might see. Once we have those information, and for each play within each game, we can then collect the first observed start and end frame and end frames for each play. So I sort of store all of this in a separate data set called tracking start end, which will consist of 4 total variables: the game ID, the play ID, the starting frame of the play, which is just ball snap, and also the ending frame, which is the QB event, okay? So we have this data frame, and then we can, once we have this, we can join it back to the original tracking data set that I named earlier as tracking, and then we can filter out everything that is not between these two instances. In other words, I filter everything before the ball snap and after the QB event. We just want to keep everything between it. Here's a little modification of correction for the frame ID, where now I want to make frame 1 as the moment of ball snap. So I did this with small modification here. But again, this is just the process of getting all the frames that you need and filter out all the unnecessary stuff. And then what we can do next, as I mentioned earlier, we can then identify the player roles within this play, in particular, who are the passer, and who are the pass rushers. Okay, so we can use that PFF data that I mentioned earlier, which has all of the player role within the play, to identify their roles. So I just simply join that data set with the original tracking data, and I name it tracking roles, just by the game, the play, and the player. And now what I can do is that I can get the passer location for each of the frame. Okay, so for each frame within each play within each game, I just want to know where is the location of the quarterback for each frame, X and Y. So I renamed those as XQB and YQB just for joining purpose later on. And finally, I want to get the pass rusher location and then join it with the passer location and then compute the two features, distance and velocity. So again, using what we just did earlier, we have all the roles of all the players. We want to keep everything with pass rush, and then let's join it with the QB location. So now we have, for each game, or for each player within each play, within each game, we know for the location of all the pass rushers and the location of the quarterback for each frame. So we can just simply compute the distance and velocity quantities I mentioned earlier. So the distance, very simple, just a simple Euclidean distance, just the square root of the differences in x plus squared plus the differences in y squared. Then for velocity, as I mentioned earlier, it's the instantaneous velocity. So we get distance minus the distance of the previous frame. So it's just the differences between the distances of the two frames divided by change in time, which is 0.1. We get the okay. And then we added a negative sign, as I explained earlier. And then strain, it's just the ratio of these two quantities. Velocity divided by distance. So now we have all the tracking information for all of the pass rushers. And we have also calculated the strain value within each play. And so now I'm going to use this data set throughout. Name it as tracking pass rush. We're going to use this data frame later on, which again, this data set features all the pass rusher info, including strain. Okay. And that is all what we did for the formulation of our measure, and we implemented it. In, I think, less than 50 lines of code, we have achieved a simple measure of pressure like that. So this is all the data wrangling and organization stuff that we did. Okay, so now moving on to how you can present the results. Okay. First, obviously, you need good data visualization. That's the #1 key for Big Data Bowl. Good presentation, good data viz. You know, the data viz should tell like a compelling story and provide some takeaway message for the audience. I think that's what they're looking for when it comes to evaluating your submission. Okay, so we're gonna create two data viz here, which I'm gonna walk you through later on. So first, we want to have an updated version of the animation of the exemplified I showed you. So remember earlier, we just have an animation where all the players are the same in terms of their point size. But now what we want is that we want to have the point size for each pass rusher representing the strain value at each frame, and we're going to animate through it. We also want to highlight our focus player, which is Max Crosby, who ended up getting the sack on the quarterback, as we saw earlier, with a different color, so that we can sort of analyze him in a little more detail. And then to accompany this first data viz, we have the second data viz, which will show how the features for Max Crosby sort of change and also interact with one another within the play. So we want to show, say, you want to have a line plot showing the distance between Crosby and quarterback, the velocity, he said he's moving towards the quarterback, and his strain value throughout the play. And then that will sort of help us look at how these features interact with one another. All right, so here are, again, quick recap, two data viz we're going to create. One figure for animating the play, and this is the line plot. Okay, so data viz number one, the exemplify animation. Again, we want to update the original figure with strain values for the pass rushers. We want to also adjust the size of each dot within the play, and also the color, since we want to highlight Max Crosby. Okay? So here, again, I'm just getting the game ID and the play ID of this play, and then I just filter out all of the NAs for the strain, which is really just the first frame, because we don't know the distance for the previous frame, so we're not going to use that. But then once we have this, we can join this with what we have earlier with the tracking information with the strain value. And here's a quick adjustment for the point color and the point size value. I tend to do this a lot in R, actually, where I create different columns for assigning value of the like the variables or the point size, the type of line, things like that, rather than just scaling them within a ggplot. I find this really helpful, so maybe you find this interesting as well. But anyway, so point colors. I want to highlight Crosby by maroon, I believe. And then I want to highlight the football yellow again. And then this is just a quick scaling of the point, where I just want to make the point bigger than the default. And I want to make the football size a little bit smaller compared to the actual players. Okay, so the whole process is just adjusting the point size and also the color for each point for the players. All right, so here's the updated figure that we just created. After we adjust for the point size, we did the same thing as earlier where we plotted the play, but instead we have a different data frame and we have different size value and color value for this play. We're also going to animate that. So as you can see a little bit of a story here within, if you look at that graph. At the start of this play, right, Max Crosby is being blocked by an offensive lineman. Right? So hence the strain value was very small at the start of the play. It doesn't change much. But later on, as he is freed up and charges towards the quarterback, you see the dot size increases and the strain value also rises as an indication of him putting more pressure towards the quarterback when he's freed up. So that's the story we can tell with this data viz. So that's the first data viz that we just made. Now in terms of the second data viz, again, the goal here is to plot the feature value for Max Crosby throughout the play. So the distance between him and the quarterback, the velocity as he's moving towards the quarterback, and his strain value throughout the play. So here I collected these features for Crosby. Since the data is in like a long format, I want to pivot it, make it taller so that we have one column for the feature value and one column for the name of the feature. And then here just extra step of relabeling and the order of these legends. And then I just plotted them with a simple line plot on each plot with GeoML, and adjusting for some colors here. So what we can tell from this data viz is that we can clearly see the interaction between the features here, right? So the strain rises as Crosby is getting closer to the quarterback, distance being reduced, and also as the velocity increases as he's moving towards the quarterback. And we see that these two are indications of an effective pass rush attempt. Closer distance and faster velocity with the pressure, the pressure increases. So this is a story we can tell with this line plot. All right, so here's a little quick mention of how you can combine those two together into one big animation. I'm not going to show the code because the code is a little bit long, but I've included this GitHub wiki on animation composition, where you can combine the play animation with the feature groups all into one figure. And then the trick here is, I guess, very simple. You just have to make sure they have the same durations in terms of the number of frames, and then you can sort of append them together using the great magic package for image processing. So if you do that, you get something like this, what we actually did for in the big data submission, where we illustrate both of these into one big figure, where we have the play animation on top and the feature curve down the bottom, illustrating how strain interacts with the other two features. So keep that in mind. This wiki is really helpful. All right. So we have created the metric and illustrated it with a simple example play of real data. So next we're going to move on to metric validation. Okay. Right, so the question here is, right, so we've created this metric. Does it actually make sense? I mean, we've sort of validated a little bit already with the example play where we show the interaction and it sort of makes sense. But what else can we do here? Okay, so we have a few questions here. So how does strain differ across different positions? Okay, so we can show that for interior rushers versus edge rushers, for example. Also, how does strain differ across different play outcomes? Okay, sack, hit, hurry versus none of those. Second thing we can ask you is, who are the top players according to the metric? And does it pass this sort of intraocular test, the eye test, right? This naive eye test. And we don't just want the eye test, right? We're statistician. We want to look at this in a little more detail. So we want to look at, how does the metric relate to previous metrics, for example? Is the metric a stable quantity over time? If you want to learn more about metametrics, this is the concept coined by Frank Snyder back in 2017. I've included a link here to their paper where they define 3 properties of a good metric for sports analytics, which is discrimination. So does the metric differentiate between players? Stability. Does the metric measure the same thing over time? And lastly, independence. Does the metric provide something new? Those are the 3 metrics defined by Frank and his colleagues back in 2020. So check out this blog post by Antonio Halber, who wrote an excellent blog post on metametrics. I think his use case was soccer, but provided some good R code and good explanation of the metric as well. So feel free to check that out. All right, so now we're gonna, I guess, answer all these questions one by one, I guess. All right. Okay, so first we have some positional strain curves. So again, the question here is, how does strain differ across different positions? Okay, so what we can do here is, I just want to get the position for each player on the field within the play. Because in that raw tracking data, that information is not included. But we know that we can get that from the players table, which has the official position defined by the league for each of those players. So we can do a simple left join to that. And here I'm looking at all the frames between the ball snap and 4 seconds, okay? Then we want to look at just interior rushers versus edge rushers. So we're keeping outside linebackers, defensive ends, defensive tackles, and nose tackles. Here's just some relabeling stuff. And then we can plot sort of that strain curve for each of these positions for each of those moments in time between the ball snap and 4 seconds after the snap. So here's what we got if we sort of run through all this code and we get this figure right here. Again, here on the x-axis, we have just the time, which here defines just the number of frames since the ball snap. On the y-axis is the average strain aggregated across all the frames. And each of these curves represent sort of an aggregated curve for each of these positions. Outside linebackers, defensive ends, defensive tackles, and nose tackles. And here what we can clearly see is that on average, edge rushers have higher strain than interior rushers. As you can see, outside linebackers and defensive ends here are higher relative to defensive tackles and nose tackles. And this makes sense because it's easier for someone who lined up on the edge to approach quarterback with higher pressure relative to, say, a nose tackle attacking the line head on. So it's a good validation geometric right there with the simple positional strain curve between frame 0 and frame 40, which is 4 seconds after the snap. Okay, that's the positional strain curve. So now what we have next is the play outcome strain curves. So the idea is similar to the position strain curve. We're going to aggregate it over all the players within the position and all the plays. And now we want to separate that big overall positional strain curve I showed into 4 different panels separated by each of the play outcomes. So sack, hit, hurry versus none of those. So here, what I did here was I first determined whether a player recorded a sack, hit, or hurry, or none for each play. Okay, so we could utilize the PFF annotation data to achieve this, where for each player within a game, we can quickly summarize whether or not they recorded any of these outcomes. Then what we can do is we can literally just use the same code as earlier, but we just need to join the outcome table to it and then added an extra faceted layer for the outcome so that we can see not just one big plot right here for the overall strain curve across all positions, but we have this same curve but broken down by the play outcome. So again, sack, hit, hurry, none of those. So this is what we get. This figure sort of illustrates sort of the magnitude of, or it sort of gives us a ranking of the magnitude of the importance of the outcomes, right? Since a sack sort of corresponds to the most amount of pressure, followed by a hit, hurry, and none of those outcomes, which is another great validation geometry. So far, that was the first validation step that we did. We did the positional strain curve and play outcome strain curves. So what we do next here is we want to rank the best pass rusher according to our metric. Okay? So our goal is to obtain a leaderboard of the top performing pass rushers based on the average strain across all frame plays, across this sort of 8-week period provided by the data. So the quick note here, we only consider the players with at least 100 snaps play as pass rushers throughout the course of this sort of 8-week period. Okay, so this first task I did here is I got these players with at least 100 snaps play as pass rushers. So just a quick filter using the scouting data, and we can identify those that played at least 100 snaps. Then we can just keep those players and then calculate their average strain aggregated across all the data across those 8 weeks, and then output the rankings with something called GT, known as the grammar of tables. Touch on that a little bit more later on. So here what we want for our operative table are the following columns. We want player name, obviously, the team, position, number of snap play, might not, sure we probably need that. And then obviously what we care about most, the average strain. Since we care most about that, we want a color gradient for that metric column for our outputted table, where the darker of the color means their value is higher. And again, I recommend checking out GT and GTX charts, which are two excellent packages for creating tables with R. So GT stands for the grammar of tables, which is sort of the table counterpart to ggplot, where the GG stands for the grammar of graphics. The theory of doing both are somewhat similar. There's some differences, but I recommend that. Also, GTX chart, I think it's written by Tom Mock. Posit. There's great tutorials there. For GTX chart, you can have different theme for your tables. So, you know, the PFF theme, the ESPN theme, whatever is out there. And also, you can, this also has the flexibility for you to put the team logo and the player logo into the table as well. So those are some additional features. Okay, so now, again, we can just simply aggregate the average strain with this code right here, and then we can just arrange the players by descending order of the average strain and rename all of these columns right here. Player, team, position, snaps, play, and average strain. So first, we're gonna look at the top 10 edge rushers according to our metric. So again, outside linebackers and defensive ends only. So after we have aggregated all of the average strain, here we're only keeping outside linebackers and defensive ends, and we're filtering out the top 10 using the slide underscore family and all, just sneakily a pretty good family within the tidyverse and dplyr. And then we can make it into a table with GT. And here are some additional formings that we can do with GT. 2 decimals for average strain. And then here's how you can achieve this color gradient for this average strain column, where I want the palette to range from light green to dark green. And then adding in extra features like title and subtitle to the table. So when we look at this table, right, it's sort of passes the eye test. We can see all of their familiar faces here as the top-ranked pass rushers. You know, we got Myles Garrett in here, top-ranked defensive end. T.J. Watt ended up winning Defensive Player of the Year that season. You know, Von Miller's in here. So overall, this is a good validation, and we can say that this sort of ranking passes the eye test for our edge rushers. What about interior rushers? We can do the exact same thing. Instead, the only difference here is we kept the defensive tackles and nose tackles, and we want the color gradient to range from light blue to dark blue. And once we get this, as it turns out, Aaron Donald came out on top as the top-ranked interior rushers. So anytime you have some sort of rankings of defenders and Aaron Donald comes out on top, you can say that you're doing a fairly good job of evaluating the defenders. And as you look through this, you see Chris Jones in here is another good pass rusher, good interior rusher. So again, the interior rushers also, with the results here, also pass the eye test and give us great validation to our metric. So up to now, this is what all we did for the Big Data Bowl. So we did the 2 figures, the positional strain curve, and these ranking. This is all what we did for Big Data Bowl. And then after Big Data Bowl, we added more, and then we ended up turning this into a paper. So here are the additional things that we did to validate our metric even more. So first we want to see the predictability of strain as a measure of pressure. So we want to correlate strain with a simple measure of pressure rate, which is defined as the total hits, sacks, and hurries per snaps. Okay, so we want to see how well these two correlate with one another. So first here, we can just obtain the hurry, sacks, and hits information for the PFF scouting data, which for each player over the course of the data, just simple aggregation to tally up how many total hurry, sacks, and hits they have from PFF data. What we can do next is that we can join it with a tracking data and then calculate the pressure rate. So ultimately, what we're going to end up here is a table with, for each player across this provided data, we want the average strain and the pressure rate. And we can aggregate them easily using the formula I mentioned. The pressure rate is just the total hits, sacks, and hurries per snap. The average strain we did earlier, we just aggregated across all frames. So we were to compute the Pearson correlation of these two variables. We see that the value here is moderately high. So we can say that strain is somewhat predictable of this pressure rate measure. We can also get a scatter plot of this to get a nice visual of how well these two things correlate. So here I just added the position to the data that I just created, and then I just plotted. So on the x-axis, the average strain, on the y-axis, pressure rate, and again, each of these dots here represents a pass rusher with at least 100 snaps played throughout the course of this provided data. And then the points are calculated by position, outside and backers, defensive end, defensive tackles, and nose tackle. And again, this also reflects the strength of the correlation value that we showed earlier, 0.61, which is a moderately high correlation between strain and this pressure rate. So overall, we can say that strain is predictive of pressure, which is another good validation to our metric. I think the last question that I asked in that first slide about metric validation was about stability. So in particular, the question we're trying to answer here is previous performance predictive of future performance based on the metric? Or how much does our metric vary over time? Okay, so in particular, in our context, what is the correlation between a player's performance on a metric, the first and second halves of the provided data? Okay, so we're going to split the data into two different parts, first 4 weeks and last 4 weeks of the first 8 weeks of the 2021 season, and look at the correlation between their strain values. Okay, so here we can just obtain the average strain for the first 4 weeks of, it's not the 2020 season, of the provided data for the 2021 season, which is the first 8 weeks. So ultimately what we want to end up here is for each player, we want in one column the strain value, the average strain value for the first 4 weeks, and also the average strain value for the last 4 weeks. And then here we're just doing the same sort of aggregation, except for we added an indicator here for whether or not the play in the game belongs to the last 4 weeks or first 4 weeks, and then we can just aggregate it based on our variables. And so if we were to compute a correlation, again, Pearson correlation between first 4 week, last 4 week provided data for average strain, we observe a pretty high correlation here of 0.86. So strong positive correlation between the average strain. And if we were to plot this, we get this nice scatter plot showing how the magnitude, how strong this relationship here is. Where on the x-axis here, again, average strain for the first 4 weeks. On the y-axis, we have the average strain for the last 4 weeks, and this scatter plot reflects the correlation value that I showed earlier showing that strain is highly stable over time and that pass rushers appear to carry the strain value down over time, which is a great validation given how strong this correlation and which also illustrates the stability of a metric. Another question we can ask here that I didn't put, which I'm not going to illustrate for the sake of time, is strain predictive of pressure than previously observed pressure itself? So here's a little exercise that you might want to try after the workshop. So we're going to plot two scatter plots here. First, pressure rate for the first 4 weeks versus pressure rate for the last 4 weeks. Okay? Now the second plot here is the average strain for the first 4 weeks versus the pressure rate for the last 4 weeks. And we're going to know which plot here depicts a strong relationship. To ultimately answer this question, again, is strain predictive of pressure than previously observed pressure itself? And the answer to this question, as it turns out, is yes, strain is more predictive of pressure than pressure itself, as we showed in our paper. Again, you feel free to, the code to these are pretty much the same as the code to the previous two plots that I showed. You just need to modify a few things, just the variables. And ultimately, you're going to end up doing this, where on the left here, well, first of all, for both of these figures, on the y-axis is the pressure rate for the last 4 weeks. On the left, on the x-axis, the pressure rate for the first 4 weeks. On the right, on the x-axis, is the average strain for the first 4 weeks. What we can see is that the average strain for the first 4 weeks sort of yields a high correlation when we plot it against the pressure rate for the last 4 weeks compared to the pressure rate itself. And as an analogy, you can think about baseball. What I mean by this is strain to pass rushing is like exit velocity to hitting in baseball. So exit velocity in baseball is kind of better than some counting statistics like batting average, strips out all of the noisy nature of those observed outcome. And here we show that strain is sort of better than this pressure rate in terms of predicting pressure. And the pressure rate is based on the observed outcomes of sacks, hits, and hurries. Okay, so for the remainder of the talk, I'm going to talk about this multi-level model for strain. I'm not going to show the code here because the entire process is a little bit long, but the code, I have a link included in here for a paper in the GitHub repository. So I'm going to quickly talk about this multi-level model for strain. Okay. So what are we doing here? So we want to sort of predict the average strain for pass rush at play level. That's going to be our response variable here. We also control for these following random effects. So we have the pass rusher, pass blocker, defensive team, and offensive team. We also control for the following 6 effects. So the number of blockers involved in play, because see a more protective scheme with more blockers can ultimately yield a lower amount of pressure. We also account for the position of the blocker and the rusher to account for any positional effects. We also control for a bunch of play context information, the down, yards to go, and also the current yard line for the play. And also what we want to do for this multi-level model is that we want to gain some notion and uncertainty in the estimates for these player effects. Okay, so we're going to perform some bootstrap, okay, some resampling via bootstrap to get that notion of uncertainty. So again, we're going to capture the uncertainty in the estimates for the player random effects. However, it's unrealistic to just bootstrap the individual play. okay? Instead, we want to bootstrap the team drives within the games because, this preserves the fact that, the schedules are fixed and the plays within the drive should go together due to their dependencies and how that impacts player usage. Okay, and again, as I mentioned, I'm not going to go too deep into this stuff, but if you want more detail, feel free to check out our paper and also the GitHub repository for all the code. And then ultimately, what we have here for this sort of multimodal result is this distribution for the estimates of these player effects. So here we're plotting the results out of 1,000 bootstraps for the variance intercept distribution for each of these players, and the players are ordered by their median variance intercept. And we sort of broke this down into 4 different pass rushing positions: defensive ends, outside linebackers, defensive tackles, and nose tackles. And compared to the previous rankings of just average strain, here we control for different variables like positional effects, play context, etc. And at the end of the day, we still see these different names, these similar names that came on top. For example, defensive ends, Myles Garrett, Nick Bosa, it's the top 2 ranked defensive ends. Outside linebackers, T.J. Watt and Alex Highsmith. Both played for the Steelers. For the defensive tackles, Dono and Chris Jones. And if you look at nose tackles, Vita Vea, etc. So overall, this is another good validation to our metric with this multi-level model fit. All right. Okay, I guess now I want to quickly touch on some advices for Big Data Bowl to close out. So first, just do it. The data is great. If you want to showcase your data science skill, whether or not you want a job in sports or any other field, this is a great outlet for showing your data science because the data is spatial temporal. It's been smooth and clean and everything. It's a great opportunity for you to work on and learn a lot. And for the big data in particular, try to keep it simple. Don't try to do it too much. Focus on a certain aspect of the game. Say if you were asked to evaluate special teams, you're not gonna try to do everything. You're just gonna focus on, say, one specific aspect, right? And also, think outside the box and try to adapt concepts from other fields. Like for us, we did material science. There are a lot of things out there in terms of like the physical sciences, things like that. So feel free to not just throw things into a black box. Just try to do more exploration and come up with new things that you can borrow from different fields. And then slick data viz is key. Okay, and we have touched on the idea of presenting the results in this workshop. You should have great data viz, spend some time on it, and try to tailor it so that everyone can sort of tell the story from it. And then for the big data submission, try to write as you work. This applies to not just big data, it applies to research in general. As you write, the process becomes much more easier at the end, where you just have everything and you can just prune words as you work or at the end. And finally, enjoy the learning and the struggle, because you're going to struggle, believe me, when you work on these type of projects. And that's the story of research in general as well. You're going to learn a lot and you're going to hate it a lot. So, but at the end of the day, it's fun. Also want to touch on more resources here. So workshop slides from last year that Ron led, which has even more resources if you just click on these things. Then we have the sort of OG tutorial of Mike Lopez, where he touched on things like space control, things like that of big dataable. And then here, Osmo to me is this great Twitter thread on big dataable tips. Also, check out Nick Nguyen's Kaggle tutorial notebooks if you're more of a Python person. And also check out its Twitch stream during big dataable season with great resources. And also, feel free to consult previous years' finalists, winners, entries. I have all the links from previous competition here as well. Finally, I want to acknowledge my collaborators in this project. I want to acknowledge Ron for, first of all, for letting me this opportunity to lead this workshop, and also for being a great mentor and collaborator, and the one and only Gregory J. Matthews, who's supposed to be here tomorrow. So if you see him, he was the one who conceived this idea and brought me on and let me take over. So I'm very thankful for having him in my life, I guess. So he's a true hero. If you see him tomorrow, tell him that. Also want to thank our sponsor, Sumo Sports. Feel free to check out their website, follow them on Twitter, YouTube for their football analytics content. With that, just want to thank you all for your attention, and yeah, happy to take any questions.
Yeah, so we can spend next amount of time just questions you have. Is this working? Okay, it's working. All right, just raise your hand and I'll bring the microphone around for questions.
Hi. So were there other metrics you considered, or was it strained from the beginning?
Just straight from the beginning. Yeah, we were just trying to keep it simple as possible and interpretable. So, I mean, there are other things in material science that we considered later on, I guess. Some things that have to do with stress and some sort of elastic modulus stuff. But with statisticians, we're like engineering people, so don't have no background, and we feel like this is clean and simple enough for a submission, so we just ended up sticking with it. But yeah.
Yeah,
More things to be explored.
I think just to add to that, the initial submission, there wasn't even like a statistical model at all. It was just introducing this concept of strain, and Quang is a data visualization wizard. So the animations, the visuals were incredible, and that led to a very simple, easy to follow submission that ultimately was selected as a finalist. And then we added the modeling later, doing the multi-level modeling later for paper submission. But the actual big datable submission was relatively just a simple, easy to follow concept that was just presented top notch. And picked the idea and just rolled with it.
Great job, by the way. Thanks. Thanks for sharing. So one thing you mentioned when you were looking at both kind of the consistency of the metric, you said, I think you had on Pearson R of 0.86. I think you had when it predicted the pressure rate 0.61, and you said these are good values. I'm curious, how do you decide? Because I think depending on the field, a 0.6 of Pearson coefficient could be great, could be not great. So how are you making kind of that judgment call on whether this is good enough, whether you can improve, that kind of thing?
Yeah, I mean, it's a Pearson correlation. The maximum you can achieve is just a value of 1, right? And we feel that the value of 0.86 is fairly high. And so we say that, yeah, I think our correlation is highly stable in terms of that. It's because the, strain is predictive, like previous strain is predictive of future strain according to that.
Yeah, I think to add to that, it's also kind of relative to other statistics in the sport, right? Of just finding where is it standing in terms of this stable value. So what you might observe in one sport might be bad in another. And I'd say just in football, something like that high is amazing in a way. And it's part of the power of like what we can learn from the tracking data. Yeah, and like other literature of previous stats and where things were at. Yeah. Other questions? Yeah.
Thanks. That was fun. I'm wondering, a lot of this is very dependent on the quarterback position. Do you see much difference in strain if you look at under center versus shotgun?
We did not look into that, but that should be something to control for. But yeah, we have not looked into that, but that's a good suggestion. We should.
So I'm just curious, when you're looking at the velocity, are you looking at the velocity of the quarterback as well as the person's rushing? Because, the quarterback can be running away. And so there's really two players on there. And then the next thing is, could you find velocity as a function of distance? Could you actually fit some sort of formula, not like a linear regression, but some sort of maybe nonlinear formula? And the last question is acceleration. Like, when you're about to leap to get the quarterback, that last jump is, I think, what makes all the difference in the world. So 3-part question.
Yeah, so for the velocity, as I described, it's the instantaneous velocity. So although we didn't consider like the velocity of a quarterback directly, we consider the distance of a quarterback between the two frames.
So they could follow each other around, and you could maybe chase them, have them hurry, throw the ball away, but it's not closing the pocket if you're not tracking the quarterback.
Yeah. What was the second question again?
If you could find a closed formula, velocity is a function of distance. For example, if you could velocity is a linear function of distance or a parabolic function of distance, because that could maybe help you to say, look, if I've got a really good edge rusher, that guy should be positioned here. That could basically help with player selection or play selection.
Yeah, that's certainly something we can look into. But yeah.
These are free ideas you're accessing for this year's Big Data Bowl.
Yeah. Something to consider for this year, I guess. What was the third again? Sorry.
Acceleration. That basically the last leap into the quarterback's legs, or just to kind of time them up.
That's not a good idea, but did not consider that. Again, we just want to try and keep it simple. So we found distance velocity. I think this works perfectly fine. But again, something to consider for this year, I guess. But
right, because I saw that the velocity over distance strain was increasing, which is great. You don't want the strain to decrease. It just basically means that you're not going to get the quarterback. Yeah. You want to show that's increasing. That was interesting, but if you could get a functional formula, that'd be
sure. Yeah, that would be interesting. Yeah, thanks.
I can just great presentation. I'm curious, did anything stand out to you last year on the questions you got, whether from participants or club coaching staff after your presentation?
So there were lots of engineering specific questions that we got, but we weren't able to answer those type of questions that well because we don't have an engineering background. But so the takeaway is that you want to work in tracking data nowadays, having someone with a good engineering background on your team is really helpful. So so that's really something that we took away from talking to all the analytics staff and all the coaching personnel. Yeah.
And just to follow up that, and you mentioned it a bit in your presentation, but with your work now and where it's going, how would you pitch it to offensive coordinators or the analysts or defensive coordinators out there?
Well, we can simply pitch the data visualization that I showed earlier. It's like a good way of sort of within play evaluation of, say, if someone was trying to put a lot of pressure, but they didn't get a sack at all at the end of the play, that's a good way of seeing how the amount of pressure has evolved throughout the play. Say so my dream scenario is for Super Bowl, Steelers versus, say, 49ers. Say it's last play of the game, Highsmith and T.J. Watt was pressuring, say, Purdy or whoever. And then it was lots of work. So let me see. If Watt was trying to put a lot of pressure throughout the play, and then Highsmith got the sack. But if we show that graph, we can see the impact of Watt within that play. So that's the dream scenario. If one day, so I have a dream. So that's my I have a dream sort of version.
I don't think that's going to happen this year.
Really cool presentation. I have a question on like the multi-level modeling part.
Yeah.
Did you look into kind of the effects that you got for the offensive players, and if you did those pass the eye test as well?
We did. If I recall correctly, not quite, because we're also factoring in the offensive line as well. So I think we control for offensive team, offensive line, or no, what is it? Sorry. Yes, so offensive team, the pass blocker, defensive team, and pass rusher. And defensive team, yeah, it did not pass the eye test well. But again, there are a lot more modeling to be done here. This is just a starting point because we can try to model like player being on the field together, that type of like some sort of adjusted plus minus, things like that. But this is just really a starting point. But that's a good question.
Go around this way.
Yeah, thank you so much for the presentation. That was awesome. I had a question about the predictive power of some of the variables that you explored here. So it seems like there's a lot of things that maybe you can use to create projections for the next year's top 10 pass rushers based on strain, position, and the position on the field. So have you actually looked into any predictive modeling or any options in that sector?
No, we have not looked into that. There are a few issues that we have to deal with here, like in terms of modeling. We've thought about all of that, but no, we have not looked into any sort of predictive modeling. But that's a good follow-up project that someone else can do if they're interested. Some room for research. Thanks.
Hi, thank you for the presentation. It was a really nice presentation. I had one question. Can we like include the other data from like the players like high school or like college football or like how they played during that time into progressing the model further in like even more multi-level modeling based on the parameters that you have set?
Yeah, in terms of high school or college data, I mean, technically we could. The question is how we get those data, especially for high school. But you know, we can surely edit those and compare these different models and see which one's better. Just do some sort of like AIC or some sort of leave one out, whatever. But I guess the question is how we get the data. But sure, we can probably add those.
Nice presentation, by the way. Did you ever look into like which quarterbacks do the best job of minimizing strain? Because I feel like that might be a good way of like exploring QB like evasiveness and stuff like that.
Yeah, so I would say that for this multi-level model, initially we don't have the teams effects. We actually have a QB effects. I don't particularly remember who ended up on top or bottom, but we did look into that. You can literally see that old code in the repo. So if you want to check it for yourself, feel free to do so. I don't have a ranking memorized now because we sort of discarded that model. But
I think at the time Burrow got sacked a lot, so he was bad on this.
Burrow was yeah. That's true.
Hi, thanks for the presentation. I was just wondering, so does the strain metric account for different roles in a pass rush plan? Like if someone's playing contain or there's a stunt that the defensive line is running. So like if someone's goal isn't necessarily to get to the quarterback, but rather open space for another pass rusher?
I mean, for the metric itself, I guess no, because it's just velocity and distance. So we didn't count for that at all, but we could do that with some sort of modeling. But no, for the raw metric, we didn't consider that.
It would also be interesting to look at just how does strain vary by those types of calls.
Exactly, yeah.
If we talk to someone that actually understands football, because we don't.
We think we are, but we don't.
Other questions? Oh, over there.
On a related note to that, I didn't hear you talk about number of blockers that were engaged. Do you have how hard would it be to control for, to include whether you've got a guy consistently double blocked or single blocked, or guys that by good scheme come through unblocked more often?
Yeah, I don't think we consider that at all. We just consider the total number of blockers involving fighting with a PFF, but no, we didn't consider any of those additional things that you mentioned.
Yeah, I would say that's a great question of just like trying to infer at a moment of time
Who is blocking?
who. The mic kind of went out on me there for a moment, but
Matchup assignment.
yeah. Any other questions?
Good question. Let me see.
I saw it. Don't worry about the Zoom stuff. We can deal with that afterwards. Any other questions from the crowd, whether it be topic or just big datable? Okay.
Hi, thank you for the presentation. I was wondering sort of how like the players' like physical attributes are accounted for within this modeling framework, because I know that you've encoded velocity, but how does that translate to like the forces being generated, I guess, like by these players, because there will be strength differences between all of these different players.
Yeah, that's a great question. Right now, we don't consider those at all. Could they even be possible to generate that much strain given their force or their weight or their height, etc., their physical attributes? But yeah, we didn't consider that at all, but something to be worked on, right on, I guess. But yeah, I haven't considered that.
Like you will for this year's Big Datable.
Yeah, there you go.
Hi, I'm wondering, do you consider strain complementarity? Like a player might not have elite strain distribution, but he might be good at maybe enhancing strain of teammates, pass rushing teammates. Do you consider any issues with that, or might you in the future? I would say that might be down the road if you would consider that, but
Yeah, that would be something to consider later on, but yeah, we haven't considered any like people getting credited for their strain because of their teammate or any of the correlation within the pass rush unit at all, but that's certainly something to be considered.
Hi, thanks for the talk. So I was wondering, like, I think in your just the raw strain leaderboards, Leonard Floyd was like at the top, and then I couldn't find him in the multi-level monitoring leaderboards. So I was wondering, like, do you have any like explanations for why that might be?
Leonard Floyd, I guess when we control for these different variables, factoring in like, the position and all these contexts and stuff, just didn't perform well. I don't have a particular explanation because but not that I can think off the top of my head right now, I guess.
Did you ever look at it from like an O-line's perspective? Maybe least strain allowed for O-line or something like that?
Yeah, that's a different version you can think about, but no, we did not look into that from that other perspective, but that's a good point though. Like, you could do it completely from the other point of view.
When did you start working on the Big Datable last year?
December 21st at like 3 p.m. when Greg texted me, and then finished it sometimes before the deadline. So yeah, that's another thing with Big Datable. Like, most people start late.
You could start early.
I was a first year student, PhD student last year, so I didn't even think about haven't thought about doing it at all. Like Ron literally asked me a question. Do you want? I think you can still do it. Like he asked me the question like early December. I was like, yeah, I'm gonna wait till next year. And then the legend of Gregory J. Matthews sort of texted me, and the rest is history, I guess.
Any other questions? I would strongly encourage students to start thinking about the Big Data Bowl earlier before December. And then semester ends and you crank it out. But let's thank Quang for the time. We'll stick around and answer any other questions. So you can feel free to hang around for a bit. I'd ask be out of here by 7 p.m. And then tomorrow morning, we'll be back here. This will be the main conference room. As you can see, there are a lot of people in this room filling it up already, and there's going to be a lot more people here tomorrow. So there will be an overflow room broadcasting the talks right next door to the Steinberg Auditorium, just because of the space issue that we have. But just try to get here tomorrow morning, get here on time, and we'll be good to go. Please let me know if you have any questions. I'll stick around for a bit. And thank you all for joining us tonight, and thank Consumer Sports for sponsoring.